Good morning. In sections 5.4 through 5.7, we're going to continue our discussion of descriptive statistics. This material is important and pretty easy, I think, so that should be good news. In sections 5.1 through 5.3, we talked about descriptive statistics as it relates to graphical displays. You have a list of raw data, you're trying to boil it down graphically so that the story behind the numbers can start to come out. In these sections, we're going to do the same thing with numerical descriptors, averages and measures of spread and so on, and we'll also do some more graphs that are related to those types of measures. So, first thing to talk about are what are called measures of center or averages. First of all, a warning that in statistics an average can mean either the mean or the median, or perhaps something called the mode. In everyday life, we usually use the word average to refer to the mean. So in this course, I will try to refer to mean when that's what I want to talk about, median when that's what I want to talk about, and the word average will refer to either one of those. As you know, the mean is computed by taking the sum of the values and dividing by how many there are. And the median is the middle number in a list that's been sorted. Let's talk about some notation here. For sample size, we're going to use the letter lowercase n. Now the formula for the sample mean can be written as follows. It's a fraction, and on the top we're going to add the values together. Mathematically we write that with a summation symbol. This is read sigma. It's a Greek letter, but it just means sum or add together. And then I write sum of the x values, just means add the data together, divided by the number of values we've said we're going to call n. For the sample median, let's use the notation capital M. And let's look at an example. Find the mean median of the number of home runs per season hit by Mark McGwire, this list. Okay, so for the mean, simple computation, although you're glad if you have a calculator to do this. So 49 plus 32 plus 33 plus ... I won't write them all, plus the last one, 29, divided by the 15 items that there are, is 38.7 home runs. For the median, I look for the middle number, but notice that the list is not yet sorted, and so the first thing I should do is just that. In increasing order, these numbers are 9, 9, 22, 29, 32, 32, 33, 39, 39, 42, 49, 52, 58, 65, and 70. 70. As we're computing these, you might mentally make a note of how easy or difficult this is in terms of just amount of work to do by hand and perhaps amount of work to do for a computer. If I look at this list, the middle number is right here, this 39, and so the median is exactly that, 39 home runs. Okay, we talked before about the fact that Mark McGwire's home run totals had a couple of outliers, these 9s. One was due to the baseball strike, and one for Mark McGwire's injury. He was injured a particular year. Suppose we decide the following. We decide that we should not count the season where which was ended early by the baseball strike, but we decide we will count the season in which McGuire was injured. In other words, I'm crossing out one of the 9s, I'm leaving the other. Why delete this year? Because McGuire had no control whatsoever over the baseball strike, presumably. Now let's recompute. And so for the mean, now 9 plus 22 plus 29 plus and so on up to 70, divided now by 14 items. This is 40.8. And for the median, here are the numbers. They've already been sorted. And there are an even number of numbers this time. There are 14 of them, so there's no middle number. In fact, the middle falls right between these two 39s. So you may remember from before, if you have that situation, then what you're supposed to do is take the mean of the middle two numbers. If there's an even number of data items, the median is defined to be the mean of the middle two. And so I should take 39 plus 39 divided by 2. Of course, that's just 39. Why am I doing this? Let's answer a couple of concept questions here. Which measure of center is most affected by outliers? So the 9s were an example of an outlier, numbers that were pretty far away from the rest of the numbers in the data set. The mean, notice, went from 38.7 to 40.8 when I deleted the outlier 9. Whereas the median, in this case at least, didn't even change at all. 39 stayed at 39. If you think about a more extreme example, what if this 9 had somehow been a huge outlier? Maybe instead of being a 9, it was a 9 million or something, and it'd be an outlier way out here at the high end. What would that have done to the mean? It would have raised it dramatically. When you're adding things up like this, if you have a huge number anywhere in the list, the sum is going to be large, and so the mean would be dramatically raised or lowered depending on whether your outlier was a high outlier or a low outlier. But the median, notice, wouldn't be affected much at all. In fact, it wouldn't be affected at all. The computation for the median here only uses the middle number or numbers, and so this outlier could have been as small as I want to think about or as large as I want to think about, and still the median would have been 39. So which measure is most affected by outliers? Definitely the mean, and that's something to think about. We discussed before that you have a decision about whether to retain or throw out outliers. One of the reasons that's an important decision is that it really affects how the mean is going to turn out. And so, which measure of center is commonly used for data with a highly skewed distribution? For example, we did income last lecture, and the distribution was very highly right skewed. For that reason, typically if you read news articles about income, you will read about the median income instead of the mean income. Again, the reason is that people like Bill Gates, who make a lot of money, would tend to raise the mean, skew the mean much higher than it would otherwise be. They don't change the median, and then the argument is, well, Bill Gates is not a typical person. If I want to really talk about what the most typical income is, if I want the average income in a representative sense, then it might be better to use the mean rather than let Bill Gates play games with the it might be better to use the median rather than let Bill Gates play games with the mean. Let's look at another type of example. Related to means are something called weighted means. Suppose the scenario is as follows. I have a car, of course, but I don't know anything about the mechanical workings of the car. I do know that it has something called oil, and that's supposed to be changed once in a while. So I decide to check around and see how often people recommend changing the oil. I talked to Ford, a spokesperson from Ford who made the car, and she suggests 3,000 miles, change oil every 3,000 miles. I talked to my mechanic. He says every 2,500 miles. I meet Bill Clinton on the street here in Marion. I think he likes to go to McDonald's. I met him at McDonald's, and we don't have much else in common, and so he suggested every 2,000 miles. I talked to a math professor across the hall from my office. He said 5,000 miles. I have this system worked out with my dog that whenever I need a important number, I talk to him and say count the number of times he wags his tail in 1 minute and then multiply by some appropriate scale factor and get a number. And the dog's answer turned out to be 1,000 miles. And then the person walking down the sidewalk outside the building here said every 4,000 miles. Alright, I have a list of numbers. They are different numbers. They come from different sources, and the question is how to combine these numbers into a single answer, because I need a single answer. I'm going to be changing my oil one time. So I could take these numbers and compute the mean, but if you think about it, that may not be the best thing, because if the car is made by Ford, then a Ford spokesperson might have a better idea of what's going on, say, than somebody like a math professor who doesn't know very much at all. So what we typically do is assign weights to people's answers. Let's call the number of miles a variable x. Let's call the weights a variable w, and then we'll work with this formula in just a moment. The weights work as follows. They need to be positive numbers. All weights are positive numbers, and they're all relative to each other. So, for example, I can take the person on the street and say, okay, that's as typical a person as I can get. I'm just going to arbitrarily assign that person a weight of 1. And then everybody else's weight is referenced to that. So if I think a person's opinion should be 3 times as heavily weighted or heavily considered as the average person, I can assign that person a weight of 3. Or I can assign a person a weight of 0.2 if I think that their opinion is only 1/5 as valuable as the average person. So when I teach this course in class, I have students give their estimates of weights, and that's an interesting choice. Since this is a canned lecture, I'll choose. Compared to the person on the street, I might weight the Ford spokesperson 4 times as valuable of an opinion as the person on the street. And likewise, my mechanic, maybe 4. Bill Clinton, well, Bill Clinton doesn't drive a car probably, let alone be responsible for its oil changes, so let's give him a weight of 0.5. And everybody knows that math professors know nothing at all, and so 0.1. And my dog, in order not to hurt his feelings, let's give him 0.2 weight. Those were subjective choices. You might have different ones. Now, come up here to this formula. This tells you how to compute the weighted mean. Remember, the sigma symbol means add things together. So in the denominator, there's a sigma w. That means add the weights together. So I come to this column, add these numbers together, and get 9.8. On the top, there's a symbol that says add together a w times x pair. So that means I want a column where I've taken the weights and their corresponding data values and multiplied them together. So I'll do this one at a time down the rows of the table. Here's 12,000, 10,000, 1,000, 500, 200, and 4,000. And then the formula tells me to add those together, and I get 27,700. So the weighted mean then is 27,700 divided by 9.8, and that turns out to be, to the nearest mile, 2,827 miles for the weighted mean. Just as a sanity check, that's about what I expected. The people that I was giving the most weight to, the auto manufacturer and the mechanic had estimates in the 2,500 to 3,000 mile range, and so the weighted mean is probably going to land fairly close to their estimates because I gave them large weight. Whereas the math professor, who's way out there, I didn't give much weight, and so he's not able to contribute very much to the answer. A more useful example and common example of this is what's called your grade point average. At the end of a semester, when you have, say, 4 or 5 different classes, the registrar's office takes your grades and computes a weighted average of them. The weights are the number of credit hours. So if you take a PE class that's 1 credit hour, that doesn't influence your GPA as much as a Gen Ed class that's 3 credit hours. And so in that situation, the weights would be the number of credit hours, and the data items would be the GPA points. So like a B is a 3.0 and a B plus is a 3.3 and so on. Now let's change gears and talk about another way in which we want to describe data. We just finished talking about describing data with averages. What's the typical number? That doesn't tell the whole story. Here's a silly example, but one that makes a point. Your doctor orders you to take 50 milligrams of a sedative at bedtime. You can't sleep, apparently. And suppose you're really paranoid, and so instead of just getting 1 prescription, you get 3 prescriptions. Maybe you go to 3 different doctors and get a sedative sleeping pill prescription from each of them. This actually happens quite a bit. It's a serious problem in America. Multiple doctors prescribing medication for the same patient. All right, you get 3 bottles of sleeping pills from 3 different companies, and then you're really paranoid, so you take a sample of 4 bottles from each of the 3 brands, and you take them to a lab and have them analyzed for the amount in milligrams of the active ingredient in each of these sleeping pill tablets. You're supposed to get 50 milligrams of that active ingredient. That's what each of the 3 bottles actually indicates that are in their tablets. And a very horrifying story comes back from the lab. Of the pills from the first bottle, the 4 pills have the following respective amounts of the active ingredient in milligrams: 0, 0, 100, and 100. So on a number line, if I do a rough dot plot of the weight in milligrams, I'm supposed to be getting 50 each time, and in fact I'm getting 0 and then 0 and then 100 and then 100. This is a terrible day if you think about it. The first night, I don't get any medication, so I can't sleep, and I have a lousy day the next day. Same thing next night, can't sleep, have a terrible day. Then the third night, I take twice as much as I'm supposed to and practically go into a coma, and so the next day I can't get up and function, and that's another terrible day, and then the same thing happens the 4th day. It's just awful. But what's the mean of these 4 numbers? 0 plus 0 plus 100 plus 100 is 200, divided by 4 is 50. This was right on. The average, the mean of these 4 numbers is exactly what the manufacturer says I'm supposed to be getting. Okay, I keep going with my paranoia, and I take the second company and analyze its pills, and I get 0, 50, 50, 100. Notice that the mean of these 4 numbers is also 50. And finally, I take the third sample and analyze it, and I get 50, 50, 50, 50, and the mean of these 4 numbers is also 50. So in each case, the company was putting out a product with a mean exactly what was advertised. But there's different amounts of variation involved here. Here, in fact, there's no variation. Everything is stacked right where it's supposed to be, whereas in the first example, there's a lot of variation. Instead of things being at 50, they're spread out around that point. Let's talk then about how to measure that spread, measure of spread or a measure of variation. Talks about how much the members of the sample differ from each other. One thing to do is to compute the range. We've already looked at that. It's the highest data value minus the lowest data value. So if I look at the data sets from 1, 2, and 3, which I'll call A, B, and C here. Here the range is the high is 100, the low is 0, and so that is 100 milligrams for the range. In the second case, the high was again 100 and the low was again 0, so another 100 milligrams. And in the third case, they were all 50, so the high is a 50, the low is a 50, and the range is 0 milligrams. Okay, what does this tell me? Something good happened here. Remember, there's no spread or no variation in the third sample, and so the range is 0. That sounds like a good thing to happen. But the range for the first and second samples turned out to be the same number. And I would argue that looking at these dot plots, there's more spread in the first sample than in the second. In the second, there was some clustering in the middle and some values were spread out. But in the first sample, everything was spread out from the middle. Problem with the range, it's not precise. In particular, not precise enough to tell that there is more variation in number 1 than in number 2. And so the range isn't used very often for these types of purposes. Instead, what you'll typically see used is something called the standard deviation. Here's the formula for standard deviation. It looks somewhat complicated and it is pretty clumsy to compute by hand. Let's do a few small examples where it's not too bad. Alright, rather than punch things all into one formula, let's break it down. And I recommend that if I ask you to do this computation on a test that you also break it down in some sort of similar way. I'll build a table here. In the first column, the X column, I'm just going to put the raw data. That was 0, 0, 100, and 100 for the first sample. In the next column, I put X minus X bar. This is notation for the mean. And in the first example, actually in all of the examples, X bar was 50 milligrams. The mean was 50 for each of these samples. So I take the data, 0, subtract off the mean 50, and get negative 50. Also here. And then 100 minus 50 is positive 50 and positive 50. Then I square these numbers. Square negative 50 and get positive 2,500, and again. And positive 50 squared is also 2,500, and again. Comment, if you're doing this on a calculator, there's sometimes some confusion. When you type negative 50 squared, the calculator will tell you negative 2,500 because the exponent gets priority in order of operations before the negative sign. You don't really mean that. What you meant for this example was negative 50 quantity squared to get the positive 2,500. That's so obvious when you're doing it by hand, but when you're punching things in a calculator, I've seen students make this kind of mistake. And it's important because what you're planning to do next is add these numbers together. If I have all of these numbers as positive numbers like they should be, I get 10,000. If I had had a negative sign in front of one of them or more, then the sum would have been different and I would have gotten the wrong answer. Let's go back to the formula now. What we've done actually is compute the X minus X bar numbers and then their squares, and then we've just added them together. So we've actually computed this number, the summation of the X minus X bar quantity squared. Now let's compute the standard deviation. It's a formula that says take the square root of a fraction. In the numerator, I put the quantity I just computed with the table, the 10,000. In the denominator, I put n minus 1, and n, remember, was the number of data values. So in this case, 4 minus 1. So that's 3. 10,000 divided by 3, take the square root, and get 57.7. And the units are milligrams. By the way, why take the square root? Because if you think about units, the units of the original data are milligrams. When I subtract off the mean, the units are still milligrams. When I square those numbers, then the units in this last column are square milligrams. And no nurse or anybody else knows what that means, and so the square root is put on the formula to get the units back to that of the data. Okay, so that number by itself tells you something, but it may make more sense when compared with another example. Let's take the second example where the data went 0, 50, 50, 100. You may want to pause the video and work this example out for yourself, the computations. It would look like here's a negative 50, here's 0, 0, and here's positive 50. So when I square 2500, 0, 0, 2500. And for a sum, this is 5000. So the standard deviation then works out to be 5000 divided by 4 minus 1 is 40.8 milligrams. Notice we were arguing that the second sample, sample B, had less spread, less variation than the first, and the standard deviation was able to pick up on that. So for that reason, it's more precise and probably more useful than the range. Third example, maybe you could think about what happens here and do this example in your head. Notice that the data values are 50, 50, 50, 50, and as they were in the other examples, x bar, the mean, is still 50. So when I subtract off the mean, I get 0, 0, 0, 0. When I square that, I get 0, 0, 0, 0. When I add those together, I get 0. And so for the standard deviation, I get 0 divided by 4 minus 1. But this is still 0, and then the square root of 0 is 0. So this is good. The third sample had no spread or variation, and the standard deviation therefore works out to be 0. Otherwise, it will be some positive number, and the bigger the number, the greater the spread. Last comment about this, the standard deviation measures the spread of data about the mean. Notice in this part of the computation, the x minus x bar, we were in fact comparing the data values with the mean. So very loosely speaking, the standard deviation acts sort of like an average distance from the mean. The bigger the number, the farther, the bigger the standard deviation, the farther the data values tend to be from the mean. Let's move on and talk about another type of measurement, so-called quartiles. These are related to percentiles, which you probably have heard about in your secondary school education. Perhaps you took standardized tests and you were reported to be at the 73rd percentile or the 46th percentile or whatever. Quartiles are special kinds of percentiles. Percentiles divide the data into 100 equal pieces, and quartiles divide data into 4 pieces. Quarter is a quarter of a dollar. A quartile is 1/4 of the data set. So if my data values on a dot plot look like this, there are actually, if you count them, there are actually 12 items, and so the quartiles divide them into 4 groups of equal size. So say a Q1, the first quartile splits the data set here, and then there's a Q2 and a Q3, and 3 quartiles actually split the data into 4 groups, 1, 2, 3, 4, and each of the 4 groups, notice, contains 1/4 or 25% of the data items. 25% of 12 is 3. You may have a question about how you decide where to put these in between. I mean, it's going to be between the 4 and the 6 for Q1, but should I put it right at 5, or what should I do? Usually data sets that I do this for are larger, and so it doesn't make that much difference. But here's a procedure. Example that I'm going to use is, suppose that 9 babies were born in a hospital one week and had the following weights in pounds. Find the quartiles of the birth weights, and then we'll also find something called the interquartile range. Okay, if you think about it, the job of the second quartile, this was to split it into 4 equal parts, the job of the second quartile then is to split off the lower half, lower 50%, from the upper half, upper 50%. We've already talked about that. The second quartile is exactly the median. And then Q1, the job of Q1 is to take the lower half of the data and split it into halves. So this is the lower 50%, and then I split it into 2 groups of the lowest 25% and the next lowest 25%. So what I should do is take the lower part of the data set after I've already found the median and find the median of that. And likewise for Q3, find the median of the upper half. So on an example, it looks like this. Q2 is, well, there are 9 data items, and so the middle number is the 5th one right here at 7.6. And then per the rule, the Q1 is the median of the data to the left of Q2 in the rank list. So I've already used the 7.6, and then the data to the left are these numbers, and so Q1 is the median of those. They're an even number, 4 of them, and so I take the mean of the middle two, 6.4 plus 7.2 divided by 2 is 6.8 pounds. For Q3, I take the numbers to the right of the median. That would be these 4. And Q3 then turns out to be the mean of 8.0 and 8.4, which is 8.2. So here are the quartiles. Then regarding the interquartile range, or IQR for short, it's defined to be the number Q3 minus the number Q1. So here it's 8.2 minus 7.6 is 1.4 pounds. And this is actually a measure of spread as well. It's sort of like the range, only it's the range between quartiles, these 2 quartiles, rather than the range over all of the data values. We'll talk more about that in just a moment. Concept questions. The IQR is a measure of spread related to which measure of center? Mean or median? And if you look at the computations that were done to compute the IQR, obviously it's much more closely related to the concept of median. Whereas when we were talking about standard deviation, those computations were much more closely related to the mean. And so in real life, when you're reporting summary of data like this, you often give a measure of center and a measure of spread, and they tend to be given in pairs. So if you choose to use the mean for your measure of center, then you typically will choose to use the measure of standard deviation, use the standard deviation as a measure of spread, and report the mean and the standard deviation. Whereas if you choose to use the median for your measure of center, then you'll probably go ahead and use the IQR for your measure of spread and report 2 numbers, the median and the IQR. They tend to go together. They do different things, the measure of center and the measure of spread, but they tend to be paired off like I just described. Why would I want to use the IQR instead of the standard deviation? Think about outliers again. Back here in the standard deviation example, suppose I found this awful pill in one of the bottles that turned out to be 5,000 milligrams or something, probably a fatal dose of this stuff. What would that do to the standard deviation? Well, if I track through the computations, if I had a very large number here, maybe this was 5,000, then when I subtract off the mean, I'd get still a pretty large number. And when I square it, I get a large number, and then that makes the standard deviation large. So outliers will greatly raise the standard deviation. Whereas if there were a large number in this data set, maybe this 18 was moved out to 18,000 or something, notice that it wouldn't affect the quartiles at all, because the quartiles are just trying to divide off 25% groups of the data. And if the quartiles aren't influenced by outliers, neither is the IQR. So an advantage of the IQR is what's called resistant to outliers. That means not affected by them. And so if you know that your data set has outliers and you know that you're not going to remove them, then you might want to choose the median and the IQR as your measure of center and spread, so that you don't avoid the skewing caused by the outliers, so that you don't have the skewing caused by the outliers. Let's look at an example of a type of graph that is related to the IQR. Let's go back to this example, and here are the babies. Suppose this hospital is in St. Louis, and here are the baby weights. And suppose I look at another hospital in Indianapolis the same week, and babies born there had the following weights, and I want to do some sort of comparison between the two. Let's look at a graph, an example of a graph called a box plot to do that. And to draw a box plot, I first need to compute the so-called 5-number summary of each data set. The numbers in the 5-number summary are the minimum value, the quartiles Q1 and Q2, which is also called the median, and Q3, and then the maximum or largest value. A box plot can be drawn horizontally or vertically. I'm going to draw mine vertically. And a box plot only has one axis. And if I look at the numbers in the summary here, I see numbers as small as 3.7 and as large as 9.3. So on my axis, on my scale here, I'm going to have numbers say as small as 3 and then up to as large as 10. So here we go, 3, 4, 5, 6, 7, 8, 9, and 10, and this axis is weight in pounds. Okay, now let's draw a box plot for the St. Louis data. All I need are the 5-number summary for the St. Louis data. Just go ahead and put small dots at these values all in a vertical line. So 3.7 and 6.8 right above it, and 7.6, 8.2, and 9.3. Alright, it's called a box plot because you actually draw a box as follows. These two numbers that define the height of the box, notice were Q1 and Q3. Next thing I do is split the box, not in half necessarily, but at the median. And finally, its official name is actually a box and whisker plot. So then what I do is draw what's called a whisker from the top of the box, Q3, up to the maximum, and from the bottom of the box, Q1, down to the minimum. And there is the box plot for St. Louis, which I will label to be able to tell the difference from the other one. Now for Indianapolis, I'll take the 5 numbers and do the same thing, only notice that these numbers are much closer together than what the St. Louis numbers were. So 6.3, 6.5, 6.95, 7.3, and 8.3. Numbers like this. So draw the box, split the box, add the whiskers, and label it Indy. Box plots are typically used in multiple displays like this. That is, you have multiple box plots side by side, and then your eye is able to make some comparison between them. For example, in which city do babies seem to be born with a higher birth weight? So here I'm kind of looking at position on this scale. Who's higher? And so despite the fact that the lightest baby was born in St. Louis, on the average, so to speak, and I'm actually most closely looking at the median here to answer this question. The position of the boxes indicates that babies, for whatever reason, seem to be born with a higher weight in St. Louis, at least this particular sample. In which city is there more variation in birth weight? Now the question is about the spread here. How spread out are the data from each other? And there clearly is more spread in the data from St. Louis, much more. Last comment, we talked about the interquartile range. Its definition was Q3 minus Q1. Notice that Q3 is right here at the top of the box and Q1 is right here at the bottom. And so in fact, the box plot graphically displays the IQR right here. And for Indianapolis, it would be here. So there is a physical meaning to the size of the box on a box and whisker plot. We've talked about measures of spread or variation. The range we discarded as not being very precise. The standard deviation is very useful, but it's heavily influenced by outliers. And then we just now talked about the interquartile range and box plots which are associated with them.